Well then, quinolones. When we talk about quinolones, we talk about synthetic bactericidal drugs. Quinolones are molecules of synthesis. They are not natural molecules, they are molecules with a wide spectrum. So we have a wide spectrum of action towards them. Great negatives and great positives. They are molecules that act on the DNA of the bacteria, specifically in the topoisomerase ADN complex. They are molecules that have a high volume of distribution. Quinolones have a high volume of distribution, and that is why they can be used for deep tissue infections, bone infections, because they have a high distribution volume, and on the other hand, they also have serious adverse effects in some cases. There are some quinolones that can produce serious hematological blood effects, visual effects, visual damage, bone damage, tooth damage. So they are molecules that should be reserved for particular situations, for resistant infections, because quinolones do not experience resistance, for example, by beta-lactamases. The action mechanism is completely different. And a particularity here is the nalgesic acid, one of the first quinolonic agents. We are going to see the why of this name. The nalgesic acid that we see here was used in the past to treat urinary infections, because this small molecule is one of the first, and it is one of the simplest, and therefore had a high urinary excretion. It excreted in an unaltered urinary vein, as you see there. The nalgesic acid has a 2.9 pKa. Then it is an acid pKa. What is the acid? Carboxylic acid. That is the one that has the particular value of 2.9. Much more acid than a common carboxylic acid. 100 times more acid. Why? What does that exacerbated acidity of that carboxylic acid generate? In fact, that group is part of the pharmacophore. If the acid is replaced, the activity is lost. If there is an alcohol there, it is not enough. There has to be an acid. If there is a tetrazole, is the tetrazole isostero of the acid? Yes, but the activity is lost. That is, that acid is untouchable. Not even by an isostero I can change it. It does not have bioisostero. The tetrazole is isostero. Technically, yes, but it is not bioisostero, then the activity is lost. Well, the exacerbated acidity comes from a hydrogen bridge that it has with the carbon dioxide that is there in the wax or vicinity. If we see it now structurally developed, what we have is that the formation of an intramolecular hydrogen bridge, 1, 2, 3, 4, 5, 6, and that hydrogen bridge explains the elevated acidity of that group. And those two groups, the acid group, which will be like carboxylate to pH 7, and the ketonic group, which will be neutral to pH 7, are responsible for anchoring the target, specifically because they are going to anchor a metal. They are going to anchor a magnesium atom within the protein target. And we are gradually advancing there. Another relevant feature is that the system is a derivative of naphthalene. That is, we have two fused cycles. Two fused cycles, where in the position below, there is a nitrogen atom that is relevant for the activity, and that nitrogen atom is completely dislocated by resonance. That nitrogen atom increases the electron density of the acetone, and that is favorable for the activity. So it is not convenient for us to eliminate that nitrogen atom from the ring. It is good that carbon dioxide has a high electron density. It is good that the acid is anionic to pH 7. It will not have the proton. Be careful, that proton will not be at pH 7. Why? Because that is how a structure called bidentated is generated. A bidentated structure that is like a clamp that is anchored to a sodium atom. The resonance effect does not explain the increased acidity. It is explained by this. Intermolecular hydrogen bridge. That is what increases acidity, structural base nucleus. The structural base nucleus derives from what is known as benzoquinone. Here in the center, have a parabenzoquinone, which is a ring derived from benzene that has double oxygenation. This other is an orthobenzoquinone. It changes the position, and at the same time, as it is fused by the face, it derives from 1 to 1.8 naphthyridine. In other words, instead of being a common naphthalene, it is a naphthalene with 2 nitrogen atoms in the structure. So it is a fusion of both systems. We have the naphthalene system fused with the quinone system at the same time. Here's a question that says, how do you think these cyclic systems are from the point of view of electronic low density? What can you tell me from the point of view of the electrophilia? A benzoquinone is a nucleophilic or electrophilic system? Very well, these atoms. These 2 carbons that are here are strongly electrophilic, and if they are electrophilic, they will have a good adhesion to the topoisomerase and to the DNA, which are nucleophilic. They have made an effort to publish molecules of this type, because in general, the quinone-type derivatives that we were showing there can have an anti-cancer effect. Here is an example of several derivatives with quinones within the structure, and many of them are anti-neoplastic, anti-cancerogenic. Example, here is the mitoxanthrone. It is a synthetic derivative. We showed this one at some point for the solemn one, and we saw that it had a pharmacophore. What type did it have? If we compare it, for example, with camptothecene. Do you remember anything about that? This already had a pharmacophore where it was respected that this oxygen was at a certain distance. For example, with this nitrogen here, that these distances that were key to the activity were generated. A pharmacophore. How is that called? When there are elements at a certain distance that are key to the activity. Structural or geometric pharmacophore. Geometric, right? It gives a rubicin next to it. Another anti-neoplastic agent also preserves this system, but it is more hidden within the structure, etc. There are simpler molecules. Well, the point is that they are cytotoxic, very electrophilic. Molecules tend to be cytotoxic, either for bacteria, for parasites, such as Chagas, or for tumor cells, cytotoxic effect. And well, what the quinolones are going to do, they are going to join. They are going to link to the complex ADN topoisomerase. And in this way, the multiplication of the bacteria is then prevented. But this is different from what the macrolide does. Be careful, the macrolide is linked to the ribosome, the 50s units. This is linked to the topoisomerase in conjunction with the Haps ADN. So it is a complex interaction again, because we are going to have the ADN of the bacteria, the topoisomerase, and in the middle, the quinolone blocking or interfering with that process, blocking the unrolling that makes the topoisomerase of the ADN of the bacteria, so that it cannot be reproduced. And new antibacterial quinolones are always being investigated. Why? Because many of them are very resistant. That is, there is no resistance against them. And on the other hand, because they have a high action spectrum. Here, there is a scientific article where they report the union of 2 systems of a heterocycle called benzimidazole to quinolones as powerful antimicrobial inhibitors of DNA with the complex with topoisomerase. And how is that union? What does it do? Here are some key data from the article that later you can fully review. It says that the prepared quinolones had a strong antimicrobial effect and a wide spectrum. Some compounds showed anti-activity. What was it? MAC, Staphylococcus aureus, methicillin resistant, which is a major public health problem today. Well, these quinolones destroy this type of bacteria total. The induced bacterial resistance by the target compound was much less than that of all clinically reported drugs. Okay, so let's go to the interactions now. From there, with this, we are going to finish this short block so that you have time. Look, there if you look, you can see part of what it is. In yellow, the quinolone. This orange strand is the DNA. It is a simplified DNA. In green, the topoisomerase rests. So there we have three things. And in the center, there is an atom of magnesium. What load does magnesium have? Physiological pH? Positive +2. Then magnesium plus torpidity. Let's get closer now. Here we have another visualization. These rods, what are they? It is an ultra-simplified representation. Those rods that go here, with the orange-colored chain, look, they are here in front too. The nitrogen bases of the DNA. And second, in yellow, the magnesium atom, the quinolone interacting so much with the protein. For example, with a glutamate through an interaction of hydrogen bridge with an arginine through hydrogen bridges, and at the same time, the quinolone. Look, and here we are going to get closer to this, to magnesium. Observe the following. This here is the carboxylate of the quinolone. This here is the carbonyl of the quinolone. What is the carbonyl and the carboxylate doing with the magnesium? With a clamp, right? It is anchoring. It is freezing. It is forming coordinated links and a coordination of these two oxygens to the magnesium atom. That is why if we eliminate any of those oxygens, the activity is lost. That is why it is good that down here is this nitrogen, which is an electronic hue, bound by resonance to give it density of charge to the ketonic oxygen by acid. Okay, mainly. So in that way, we have a strong anchor. And here we now erase the protein, and we leave only relevant amino acids of the protein. So the DNA is what is shown there with the sticks. Okay, the magnesium atom, the double approach of these two oxygens to the positive magnesium, that is, the coordination of acetone and carboxylate, and see how the rest of the structure also interacts with a serine bond. But that is not from the DNA, it is from the protein, right? Hydrogen bridge, arginine, hydrogen bridge to the oxygens of the carboxylate portion. And I don't know if the benzimidazole does something else there. No, here you can't see it. But here behind is the benzimidazole. Connected. This is the benzimidazole through a piperazine, and those also do interactions, but here they are not seen because the protein is there erased to that side. So that is the type of interactions that the quinolones do, and that is already part of the C relationship between structure activity and the other class. We are going to see how we can go forward in different generations of quinolones, increasing their power. Particularly by introducing halogens in the structure. Particularly by introducing halogens in the structure.